Okay, so in part two, we'll be discussing about the actual concept of ultrasound, that how it gets work, like the working procedure of ultrasound and even the calculation part of specific acoustic impedance. And in ultrasound, ultrasound waves have frequency above those audible to the human ear, that is greater than approximately 20 megahertz. Means ultrasound has greater frequency approximately 20 megahertz. It can be 20 megahertz too in some way. Okay, so talking about this frequency, here is high frequency wave and low frequency wave. So ultrasound may have both frequency, it has both frequency, high frequency and low frequency. So in high frequency, it has you can see here, it has a period, it has a less period, it has less period, and here is a lot, it is a more period. So in low frequency, it has more period, means it takes more time, and high frequency have low period and it takes more less time, okay, to travel. So what happens if high frequency occurs in our body through ultrasound? Okay, so let's see here. So when at high frequency, when the high frequency passes into our body, you know it has a greater resolution, okay? So it has a greater resolution, but depth of penetration is limited. It means that the penetration means the power, the penetration means it's the power. So the power, the penetration means how much it has passed. So when there is a high frequency, it has greater resolution, but the penetration is limited, the passing of electrons is limited. so at low frequency, it has less resolution but have greater depth of penetration in the body. So I mean, it can pass into the many organs of our body. Suppose uh, uh, let's take one example. So this is the this is the muscles, and this is the bone, and let's say this is some kind of. So when we have uh, high frequency, when we have high frequency, it gets only penetrate up to here. But when we have low frequency, it can penetrate up to here, okay? So it can penetrate up to here, but the resolution would be less. But in at here, the resolution would be high. So it has a high resolution. So principle use of ultrasound. So there is some principle to consider, so some principles are so how the ultrasound wave is incident in our body and refracted and reflected. So here is the two medium. Suppose let's say this is air, outside air, and this is muscles. Let's say this is muscles. So here is the muscles. So when the ultrasound wave is incident into the air and muscles, it gets reflected, okay? So it gets reflected over here, and then after also some of the waves get reflected. Don't think that every waves from ultrasound gets transmitted into our body. It's not. You can even say this is transmitted, okay? You can even say this is transmitted. So this is the transmitted. So when the waves of ultrasound is being incident into our body, some of the waves gets reflected and some of the waves get transmitted in our body. So this is the boundary. Okay, so this is the boundary, and here I have written the relative magnitude of reflected. The relative magnitude of reflected and transmitted intensity depends on the angle of incident. So this is the angle of incident. Okay, so this is the angle and the nature of 2 meters. So the nature of 2 meters, so here is the one ear and here is bone. So I'll talk to more specific. I'll talk to you about how it affects in next slide. Okay, so here I equals to IR plus IT. So incident incident ray of ultrasound is equal to sum of reflected and sum of transmitted. This is sum of reflected ray and sum of transmitted ray. And specific acoustic impedance. So the so in previous we in principle of use of ultrasound, you knew that the angle of incident and the nature of 2 meters. So how the nature of 2 meter affect the magnitude and of reflected and transmitted of incident. So here we have specific acoustic impedance. So specific acoustic impedance. Acoustic impedance is the physical property of tissue. So it is the physical property of tissue. So it's kind of, like property. So it describes how much resistance of an ultrasound beam encounters as it passes through the body, through the tissue. Like how much, suppose let's say in muscles is a physical, so acoustic impedance is different in a muscle. Okay, so and it also describes how much resistance an ultrasound beam encounters as it passes through a tissue. So it describes how much ultrasound is going into our body. So specific acoustic impedance is the product of intensity, a product of density of the medium, and the speed of sound in that medium. Okay, sound in that medium. So here is like specific acoustic impedance is this J. It is denoted by J and rho times C. So this is a general formula to calculate the specific impedance of uh, physical property of tissue, like for is kind of medium. Okay, so medium. So calculating reflected intensity. So how do you calculate the reflected intensity? So what is mean by reflected intensity actually? So reflected intensity, let's see. So reflect intensity uh, of coefficient. Okay, reflected intensity of coefficient. So reflected intensity coefficient shows how much the intensity of ultrasound incident. So it means that how much the intensity I is incident into the body and waves reflected, and how much the ultrasound waves reflected back. So it indicates IR over I. So how much the waves is reflected and how much waves is incident. So it is the part of some relation, and this is J1, J2. So so let's say here is the medium 2 and medium 1. So each medium has its own acoustic impedance. Okay, so it has J2. So let's take example of air and skin. So in uh, air and skin, it has about let's say um, I let's say it has about 0.995. So this 0.995 indicates that the reflected intensity coefficient. It means that it is the how much intensity of it is the fraction, okay, it is a fraction of instant intensity coefficient. You can even say that is a fraction. Okay, so how much fraction is transmitted into the body, it says this value.